Today in this class, I'm going to talk about propagation and cost function. There are many details related to generative AI, but there are certain number of fundamentals that dictate the training processes of generative AI. So one of them is backpropagation. Second is cost function. During the forward propagation, you have input vector, and through the multi-layer propagation, you will end up with probability distributions. If you give input vector of a picture of cat, at the end of the neural network, it will give you the probability of cat, tiger, or dog, or whatever. If your answer from deep neural network is not correct, then you have to do the backpropagation to update the parameters inside the deep neural network. The updating process of the parameters of deep neural network, including generative AI, is being called as backpropagation. And then when you start the backpropagation at the end of deep neural network, you have to decide how much, which direction you have to update. For example, one of them is how close your answer and real data is. And sometimes you can use entropy function and cross entropy function or KL divergences. There are many different cost functions. Cost function is a way you can put your value of your life into a deep neural network. Sometimes if you want to make a deep neural network to win an AlphaGo game, winning is your value. Some people may design deep neural network to share your profit to everybody. So depending on your organization, your company, and yourself, you may have different value of your life. That value of your thinking will be put into the cost function. And depending on how you decide your cost function, your deep neural network and generative AI will behave in a different directions. So overall, I think these two are the major important subjects to be when you are building up deep neural network, whether that is the CNN or RNN type of model, or whether it is a generative AI model, or whether it is reinforcement learning model. Because of that, I'm going to talk about this subject today and next week. For the simplicity of analysis, I'm not going to use the vector or matrix notations. I'm going to use the scholastic notation. Let's assume you have an input vector X, and you have a hidden layer, and eventually at the end, you have output. Of course, in the case of supervised learning, you have real data. If you put the input vector X into your deep neural network, the input will be multiplied by weight matrix, and that will go into a activation function. And there are many different types of activation functions, but in this class, I'm going to mainly talk about the sigmoid function. And then output of sigmoid function will be represented by hidden layer. Of course, in this lecture, I'm talking only about the 3-layer cases, But in the deep neural network or generative AI like ChatGPT, we may have 100 layers, 100 hidden layers. In the future, you should believe me that number of hidden layer will be thousands. So to make a more multiple tasks like composing music, writing texts, and making sounds, and to make that multiple functions, this layer has to be deeper and deeper. The number of parameters, W1, will become larger and larger. And then hidden layer will be multiplied by matrix W2, weight matrix, that is gonna be input of sigmoid function or sometimes softmax function. In the next class, I'm going to give you many different type of activation functions. One of them mostly used for at the last layer is softmax function. But at this moment, we are not going to talk details about that. At this moment, I'm assuming the activation function of layer 2 is a sigmoid function, then that is becoming output Y. And the process to convert input vector to output is being called as forward propagation. Then at the end of deep neural network, we have to define cost function. Sometimes we are saying it as a loss function. Basically, the cost function and loss functions are same depending on individual. Sometimes we are saying it is cost function, sometimes it is loss function. I have to say that there are many different types of cost functions. At this moment today, for the simplicity of analysis understanding, I'm using mean square error function. Instantly, you can understand the meaning of cost function. That is the difference between your deep neural network output and real number. Real numbers are induced from training data, and it has square, means it's a kind of parabolic function. The cost function will be minimal. C will be minimal when y is equal to y dash. That is our goal of training. Please remind yourself that the W1 and W2 matrix size is huge. So to determine whole matrix element of W1 and W2, we have to do a lot of forward and backward propagation. I would say so. Let's assume we have a curve. Axis is W2 and y-axis is cost. I assume we have certain functions, graphs, which relate W2 element to cost function. our goal is to bring this initial W2 to W2 optimal point. Let's assume initially our W2 value is here, but we have to bring this W to W2 optimal. In order to that, we have to update W2 with this form. At the initial point of W2, we may have a slope. If we have positive slope, we have to reduce the W2 to reach to W optimal. That's why we have minus number here. This alpha is learning rate. So step by step, we have to move this value to the optimal point. That's why we have alpha learning rate. Now let's go back to the for the propagation. If we have an input vector, we eventually obtain output. By comparing the real data, we can define the cost function. If we have certain differences between our output and real number, we have to calculate the slope of this function, and we have to decrease the W step by step. So this is the backpropagation equation. So the process to update W2 depending on the slope of the cost function with respect to W2 is being called as backpropagation. So in order to bring this W2 initial value to the optimal values, probably we may need 1,000 steps. So that means we need 1,000 iteration of forward propagation and backward propagation. That means we need 1,000 number of input vectors and y dash. So because of that, generative AI and machine learning is very computing intensive to determine this W2 optimal. When you reach to a point of W2 optimal, derivative of this cost function with respect to W2 is becoming 0. Then the training process is completed. Whether this your AI model is CNN type or RNN type or reinforcement learning or generative AI like ChatGPT, this is the same principle to make them smart. Now let's start with differentiation. Now I would like to derive equations that represent the derivative of this cost function with respect to W2. So we need an equation to put into your source programming. And in this case, I'm assuming that we are going to use the sigmoid function because sigmoid function has certain simplicity when we are doing the derivatives. So I'm going to use that. Please remember that derivative of this function is becoming, because 2 and 2, 1 over 2 is canceled each other when we are doing the derivative, then it is becoming y minus y dash. And then y dash is becoming constant. We have to do the derivative of y. Here, I'm assuming that this mathematics is just like engineering mathematics and freshman courses. So it is not very difficult. One, what I'm trying to do is to obtain slope of cost function at a position of W2 initial. If we have very steep slope, we have to jump more and more to reach to the optimal point. If the slope is very small, we have to gradually approach to the W2 optimal. So it is important or necessary to induce an equation to express the slope of this cost function. In a case of mean square error cost function and sigmoid activation function. If you are using different activation function, you may have different equations. If you define different cost functions such as entropy or KL divergences, those are mostly used for generative AI, we may have different equations. In a probably next month, we're gonna deeply go into the generative AI. Then we have to derive all these equations for generative AI. Very, very complicated. So I don't want to jump into that complicated mathematical equations, but I would rather spend more time to use the simple case to discuss the meaning of these equations. So if we do the derivative of cost function, we have y minus y dash first. That is actually coming from this. And then we have to make a derivative of y, because y dash is constant, we have to do the derivative of y with respect to W2. And I'm assuming that y is equal to sigmoid function 1 divided by 1 plus exponential minus W2h. Of course, you remember that G is between 0 to 1. Usually, sigmoid function is more suitable for classifications, whether it is a cat or a lion. Some binary decision. When you have to make a binary decision between 0 to 1, sigmoid function is very friendly equation. And then we have to do the derivative of sigmoid function with respect to W2. And you remember in the previous class, derivative of sigmoid function is represented by g 1 minus g. So that's why we have g 1 minus g. And then we have to make a derivative because input of sigmoid function is W2h. We have to make a derivative of this one. And we're going to have finally h will appear on that because of the derivative of W2h with respect to W2. So finally, we found that update equation of backpropagation of first weight vector, W2. You remember that we're going to have 100 of weight matrices to be determined during this iteration process. But initial W2 can be updated during the backpropagation using this equation. This is the initial value, updated value. It has learning rate. It has the difference between output and real data, and it's gonna be a kind of slope. So here, delta y is represented by this equation. Mostly y itself, the output value and difference between the real value and output value, and h is hidden layer output value. So if you once know y and y dash and hidden value, you can update W2. It's a kind of algorithmic equation, not very complicated because that is the beauty of sigmoid function. The slope can be easily calculated by just multiplication and plus and minus. And those numbers are obtained from the difference between your output and real number. It should be very as close as possible. But so if you have y very close to y dash, delta y will be very small number. That is the really near the optimal value. This is the backpropagation equation. So by using the gradient, we gradually approach the optimal point. This kind of mathematical approach is called as gradient descent method. If you have slopes at a certain point, you want to go to the optimal point. Even though this is scholastic representation, it will be true for the vector field as well. In the three-dimensional or n-dimensional field, if you want to reach a certain optimal point, you just move around and calculate the slope, and you change the W to make a cost function smaller and smaller. In order to do that, we use the slope to determine whether you go to left or right. You move, if the difference is large, you move further. If the difference is small number, we move small again. When you are designing your generative AI model, you have to choose certain optimization method when you are using PyTorch or TensorFlow. So there are certain variation of optimization method, but basically, I think all of are very similar to gradient descent method. Let us continue backpropagation. Now, I would like to update W1. So far, I was able to derive equations to update W2 using the gradient descent method. Now, it is time to talk about a backpropagation equation to update W1. In this simple case, I'm using scholastic presentation and just using the scalar expression of matrix W and W2, but it is actually tensor, n-dimensional vector with a huge number of dimensions. But principles are same. So now I would like to derive equations to show the derivative of cost function with respect to W1. The first term is actually coming from the mean square error function, derivative of mean square error function. And y dash is constant because that is the real number. Y is the actual output that is depending on W1. That's why we have derivative of cost function with respect W1 is expressed by this equation, y minus y dash. That is the difference between your output and real number, and the slope of your output with respect to W1. Actual output is W2 multiplied by hidden layer. We have to do the derivative of this sigmoid function with respect to W1. even though this is a little bit long derivation procedures, but what I would like to say is that this is update equation of W1 during the backpropagation process. In order to conduct that task, we have to be able to calculate derivative of a cost function with respect to weight W1. In the previous equations, we was trying to optimize W2. Now we are trying to optimize W1. So in order to do that, we have to be able to derive the equations to tell the slope of this cost function with respect to W1. So after some board processes, we reach a point of this equation. The simplicity of these equations was achieved because we are assuming the sigmoid function. The derivative of sigmoid function is just y 1 minus y. Derivative of sigmoid function h is h1 minus h. So finally, what we found is that we can determine the slope of cost function with respect to W1 by having difference between neural network output and real number. This y1 minus y is the slope of sigmoid output function that is represented by y1 minus y. You remember that y is a sigmoid function that is, we have 0 to 1 probability function. And if we have W2 is updated here. So we are using either W2 or W updated 1 and hidden layer H1 minus H. This hidden layer output can be obtained during the forward propagations. And finally, X vector, input vector. So by combining output Y and Y dash and H and X with the given W2, we can update W1. These are the update equation for W1. Even though we have 100 layers and 100 hidden layers and 100 weight matrix W1 to W100, we can derive these equations because these are sequential equations that can be calculated from W to W1. And sometimes we are saying that this kind of equation is called chain rule. In real programming, W is much more complicated. W here I'm saying W1 and W, but it is more complicated. W is a n-dimensional matrices with a tensor form. So but there are a lot of indices to when we are deriving those equations, but basic principles are, I think, well represented in this equation. Sequentially, we can update W2 and W1. With the given H and Y and difference, we can update W2. With this Y and Y dash and H and W2, we can update W1. And similarly, we can go back to the first layer weight vector. During this derivation of chain rule, I was assuming that there were two assumptions. One of them is I'm using the mean square error function as a cost function. Second assumption is that we are using the sigmoid function as a activation function. So if you choose different cost function and different activation function, all these equations will be different. But the chain rule philosophy are still there. Only details are different. Now it's time to talk about cost function. So there are 5 or different cost function representations, and today and next class I'm going to talk about that. A lot of those cost functions came from information theory, and I'm not good in information theory, but I will try my best to explain the meaning of the cost function. First one is the mean square error cost function. As I know that this is very easiest way to understand, easiest way to express, but I remember that learning speed of this one is very slow. For example, let's assume that you have this cost function. Near the W optimal, the slope of this function is very small. So when we are doing the back propagation, when W is near W optimal, the difference is really small. So slope is going to be very small. So near W optimal slope is very small. Meanwhile, when y and y dash is large, we may have large slope. But near this optimal point, I believe that slope is very small. So learning rate is very small. Second, cost function that is usually used for binary among the generative AI, there is a model named GAN, Generative Advisory Network. He is having similar cost function. Here, binary means y dash is equal to 0 or 1. That means your output vector element is either 1 or 0. If you give an input of picture, output will give you, the y dash will give you whether it is dog or tiger or cat. That is given from human. And human can distinguish whether it is dog or cat or tiger. So y dash is actually a vector of 0, 1, 1 or 1, 0, 1 or 1, 1, 0, 0, 1. This is tiger, this is cat, this is dog. Y dash is only 0 or 1, I would say this is my personal expression that is called binary. And log y is usually, I would say, entropy. Entropy is the amount of information to describe y. Usually, if you have lower entropy, if let's assume y, log y is very small number, that means you have big separation of data. If you have higher entropy, that means your output y is very fuzzy. You cannot determine whether it is good or bad or something like that. This kind of my explanation today is not probably not easy to understand, but after a certain number of classes, we will be more familiar with this entropy equation. In this class today, I'm not going to go very details about the meaning of cross entropy. And in other cases of generative AI, they are using KL divergence as a cost function. Later, probably next week or a week after next week, we are going to talk more about this cross entropy and KL divergence. That will give you the foundations to understand generative AI. But today, I'm not going to go very details to discuss cross entropy. Rather, I would look into the meaning of this equation only mathematically. Let's assume in the binary y dash, whether your picture is tiger, then y vector will be 1, 0, 0. If your picture is cat, the output vector y dash has to be 0, 1, 0. And if your picture is dog, you may have a y dash vector 0, 0, 1. Why we have to update W1 and W2 to generate as similar as these real data values? For the case of tiger 100, this cost function is just becoming minus log y. And then this cost function with the function of y is becoming like that. If y is equal to 1, that is the condition. This is condition y is equal to y dash is equal to 1. This condition. If your output of your deep neural network y is near zero, this is actually minus log y function. If you are good in mathematics in engineering, you may understand this is the minus log y graph. Actually, this is log y graph. Opposite of that y graph is representing the cost function. Let's assume that initially your W and W2 is not good numbers. So you have to update W and W2 using the gradient descent. And if this W1 and W2 is not good, this one, the right answer is 1, but if your output is near 0, you have to update this W1 and W2. You have to update using the back propagation until you reach a point of y is equal to 1. That is the condition y is y dash and is equal to 1. You remember that this slope is a logarithmic function, and that is very fast. Compared to sigmoid function of cost function of mean square error, this log function is really fast function. Derivative is really high near the initial point. So I would say this binary cross-entry function is more suitable for fast training processes. Now let's, for a case of 0 to y dash is equal to 0, then is the second element. I would say this is y1, this is y2, and this y3. Output layer has certain number of element vectors, and I'm assuming that this is y3, then that should be 0. If your picture is a tiger picture, this third element should be 0. That is the case for y dash is equal to 0. Then this graph is becoming like that. If it now we are talking about binary cases, if y dash is equal to 1, this second term disappear. That's why we only have this form. For the case of y dash is equal to 0, first term goes away, disappear. We have only second term. And y dash equal to 0. That is why we have this graph. So answer is y should be 0. Output of the deep neural network should be 0. But initially, let's assume that you have y is near 1, then cost function is really, really high. And you have to update W and W2 until you reach a minimal point where it is y dash is y is equal to 0. Let's assume that this is your income. This is whether you are rich or poor. Let's assume you have a deep neural network that is determining whether you are rich person or poor person. Unfortunately, depending on individual, it may be different. My case, even though I have a income of $1,000 in a month, I'm happy in these days. I have a family, I have students, and I have classes. But some people may think they have to have 1 million US dollar to be rich. So let's assume that we are surveying that this is our real data. We are surveying, we are asking people how much income you feel rich, or this is a rich point, and this is poor point. Whether you are rich or poor, I would say this is $1,000. Let's assume that your deep neural network have this kind of probability output. There are some separations between y and y dash. You have to adjust w and w2 to match y and y dash. Whether you are in the mathematically, you can change bias or slope of your sigmoid function to match this red line to the real data. But this is binary 0 point and this is binary 1 point. So in this area, we have some cost. That is this logarithmic function. This logarithmic function, entropy is representing the cost function when our real data is near the poor area. And the area between this red line and our real data is represented by this entropy function. Meanwhile, near the rich point, there are also separation between our real data and our CNN output. That is related to this log function. There are many different ways to explain the meaning of entropy and cross entropy. But today, because this is the first class to talk about cost function, I'm giving you a simple way. But in the next class, I'm going to explain the meaning of this cost function using the methodologies or languages used for information theory. I haven't taken any information theory class in my life, but I'm trying to explain as much as possible. So today I was talking about backpropagation and chain rule and the cost function, very important part of generative AI. And depending on different models, they have a little bit variation of cost function and activation function and chain rules, but basic principles are same. Thank you for your attention, and I hope you enjoy my class. Thank you.